Hi again. We're on lesson 1-7 today, and you can look at the title and see what we'll be discussing: combinations of functions. So composing or composite functions. We're going to basically look at doing some arithmetic with functions and then actually doing a composition of two functions. Those are different things. So we're going to begin by looking at some basic arithmetic that we can do with with the functions. We're going to begin by looking at the two functions f of x equals x plus 1 and g of x equals x. And if we combine those with addition, well, you'll probably get exactly what you expect. That is, you're going to add f of x, x plus 1, to g of x, which is x, and then do any simplifying that is appropriate. So we've got x plus x is 2x plus 1. So functions can be added by combining like terms. Same thing is true with subtraction. If we're going to subtract those two functions, f of x is the one that's listed first, so x plus 1, and from that we're going to take away g of x, which is just x in this case. Now combining like terms gives us no x's, 0 x's, and just 1 as a result. The one thing I would caution you about there is to remember it's easy to make arithmetic errors if you forget that you're subtracting everything in the second function. So if there were more than one term here, like x plus 16, you have to remember that you're subtracting x and you're subtracting 16. The next operation that we're going to look at is multiplying those two functions. And x plus 1, that whole thing, quantity, going to be multiplied by x. Really, this is a distribution. That x needs to multiply both terms inside the parentheses, so x times x, x squared, plus x times 1, x, and we've multiplied those two. Here's our last combination of functions, and we're going to combine with division this time. F of x is x plus 1. G of x is just x, and since there is not an x that can be divided out of both terms here, this is as far as we can go with this composition. We do have to remember though that this will never work if x is 0, because we can't have a divide by 0. So you can see that part of our discussion today has to be about domains for functions. For these three, no domain restrictions at all, because there's not anything to worry about with the radical there, and this is the only one that contains a fraction. So let's move on. And yep, I guess I spoke too soon. The restrictions on domains of functions: no negatives under the radical, or no negative values under an even radical, even indexed radical. So that's something that we've got to look out for. An even indexed radical. And the one that we looked at just a second ago, no zeros in the denominator of fractions. So those are two things that we have to keep an eye out for as we're combining functions. Now we're going to take a look at f of x being the square root of the quantity x minus 3, g of x being the function square root of the quantity x plus 1. When we add those two, root of x minus 3 plus root of x plus 1, really, folks, we're stuck here. These are not like radicals. They can't be added any further. So all we can do is show that we could add them. As far as domain restrictions, we need to look at both of these things separately and then decide which of them is the most restricted, because we have to choose the most restrictive domain. That is, you want to err on the safe side. So choose the most restrictive domain. And let's see, the domain for this radical, well, if you had 3 for x, that would be okay. But if you have anything less than 3, you're going to run into the negative under the radical thing. So for just this part of it, x has to be greater than or equal to 3. For just this part, An x of -1 would be okay, because that would give us 0, and the square root of 0 is okay. But anything less than -1 is going to create a problem here. So in this one, x has to be bigger than or equal to -1. And if we're adding these two, then what we have to do is choose the most restrictive domain of the two that are there. And this one, x greater than or equal to -1, so I'm going to look here first. Greater than or equal to -1 would mean we can use values -1, 0, 1, 2, 3. This one would say, no, you can't go those low numbers because they won't work here. You got to be 3 or more. This is the most restrictive. So it becomes the domain for this. The domain is all x such that x is greater than or equal to 3. It's the most restrictive of the two domains. And I think we'll see the same thing over here. This just calls for us to look at a division of these two. Root x minus 3 over root x plus 1. And we're not supposed to have that radical in the denominator, so the best thing that we could do we want to rationalize. So we're going to multiply the top and bottom of this fraction by that same thing. That's the thing that will get us root of x plus 1. A perfect square in the bottom. Now we've got a little bit more work to do here. Radical x minus 3 times radical x plus 1. We can use the box method to multiply this and put our result all under the same radical, since this is two things being multiplied together. It's okay to do that. Let's see. We're going to multiply the number parts of these and put it under a big radical. X times x, x squared, minus 3x plus x minus 3. So let's see, here we go. We're going to have x squared, collecting like terms, minus 3x plus x, that's minus 2x, minus 3. All of that over x plus 1. And if you think about the possibilities here, the things that are not allowable are negatives under this radical, or having this be equal to 0, having the denominator equal to 0. So the things that will make negatives under here, we can go right back here and say, well, if x is bigger than 3, we're okay. So we can't have x's less than 3. Same judgment that we made here. Our x's cannot be less than 3, and that takes care of x not being -1. So the domain for this one is the same as the domain for the previous problem. The most restrictive of the domains of the two input pieces. X must be greater than or equal to 3. Okay? Good problem there, good problem. All right, let's go on. And now we want to talk a little bit about composing two functions. This is something that you should have done in your algebra class. There are two ways to talk about composing two functions, and I'm going to suppose that we have a function f of x and a function g of x. The two different notations for saying composite are these: f of g of x, or f and then an open circle g of x. Both of those mean take the g function and use that as input to the f function. So I want to just make this clear. Order is important. Since the g function is the second one mentioned in each of these, we take the input from g and plug it into f. So when we compose two functions, we use the output of one as the input of the other. All right, one more time. We use the output of one of the functions as input in the other function. And you may have seen a problem like this previously. My daughter Allie does not work at a clothing store. However, I used her name here. For example, suppose Allie works at a clothing store where a 30% off sale is happening. Allie gets an employee discount of $10 off each purchase. And those are two separate things that are working in her favor. I'm going to let f of x be the 30% off sale. So that would mean, okay, so now I got to just show you how I think about this. If the original price is 30% off, it would be the original minus 0.3 times the original. And if you think about that, folks, combining like terms, since those both have original in them, 1 minus 0.3, really what she's paying is 70% of the original cost. That's just a slightly different way of looking at it, and that's good for this function notation. So I'm going to let f of x be the sale, which means it's the function 0.7 of the price, and x is going to be the price. Okay. G of x, well, that one says she gets just $10 off of what she buys. So however much it costs, x, we take $10 off. So we've got two mathematical expressions for each of these discounts. Allie wants to buy a $70 pair of jeans, and this says find us f of g of x, which means we would take the outcome of the g function and use it as input to the f. So I'm going to write that this way. We want f of, and remember we're working with a 70 here, we want f of 70 minus 10. That's what the g function says to do. Use your x value, subtract 10. So we really want f of 60. And f of 60 would be 0.7 times that 60. And you can do that in your head or with your calculator. Okay, so 7 times 60 would be 420, but we need one decimal place. So if Allie went this way, she'd spend $42 on those jeans, and that's doing the $10 off first. If we went the other way, and notice we use the different notation here, g of f of x, that means that we have to do the g function to, and remember, those jeans are $70. We have to do the g function to the f thing. So now we're talking 0.7 times 70. And let's see, 0.7 times 70 is 49, right? The g thing to 49 is what we have to do. We took the output of the f function, so this one is the f. We put it as input to the g. And now the g function says, well, you take the quantity minus 10. So we'd be looking at 49 minus 10, or $39. And many of you probably could have answered this question first. Allison's best bet would be to do the 70% discount first, because you're taking more, or you're taking 70% of a bigger number, and then take $10 off of that. So we compose those two functions by finding the output of one and using it as the input into another. Let's take a look at that a little bit more closely. You notice that we didn't have any domain restrictions there. There wasn't any square root or any fraction to worry about, but the rules for the domains of composite functions is the same, is to use the most restrictive domain. Okay, the one that is the most restrictive is the one that you want to choose. All right. Suppose that f of x is x minus 4, so now we're getting away from the words and into some true algebra, and g of x is x squared minus 2x plus 6. First off, we're asked to find f of g of x. Well, nobody's telling us what x is, okay? So that's a little bit different than the previous problem. We knew about the $70. We don't know here. All we do know is this says take the g function and use it as input in the x. Take the g and use it as input into the f. So all of that, x squared minus 2x plus 6, has to be put, I am going to do this circling thing, all of that has to be put in as the x in that. So we're talking x squared minus 2x plus 6, that's the g function, as input here, and then we take away 4 from it. So we think to ourselves, oh, that's not too bad. Collect some like terms. We've got x squared minus 2x plus 2 if I did the math right. All right, the next one says, I'm going to change color of ink here. The next one says find g of f of x. So now we got to take the f function and use it as input to the g. So this time we have to take this x minus 4 and use it wherever the g function says x. So I'm thinking this might be a little bit more complicated. We're going to have an x minus 4 squared, right? Wherever it said x, we use x minus 4, minus 2 times x minus 4, and then plus 6. Now, the algebra here is a little bit different, but if you remember your factoring patterns, that x minus 4 quantity squared comes out as x squared minus twice of this, so minus 8x plus 16. That's that perfect square trinomial right there. Doing the distribution here, minus 2x, and then minus 2 times minus 4 plus 8, and then we still have that 6 on the tail end, and now we've got to get our like terms wrapped up. We only have the one squared term, minus 8x minus 2x. That is minus 10x. Then we have 16, a plus 8, so that's 24, and a plus 6, 30. Okay, good, and we've composed these things both ways. Now, the next instruction says, find g of f of 2. Now, like we had $70 before, now we know what input value we're using. We're using 2. And we've already done the composition of that right here, I believe. G of f of x says that you should take the x thing, which is 2 in this particular problem, and square it. Then do minus 10 times of it, so minus 10 times 2, and add 30. And if we work the arithmetic out, we're talking 4 minus 20 plus 30. I'm thinking 14 here, but you can check my math and see how I did. Okay, 14s. That's going to wrap up our lesson for today. I'm going to encourage you to get to that U-Try as quickly as you can.